Thank you, Professor Kulkarni. It's my pleasure to introduce my colleague, Professor Udayan Ganguly. Just to give some introduction, Professor Udayan Ganguly received his BTech degree in Metallurgical Engineering from IIT Madras in 2000 and the MS and PhD degrees in Material Science and Engineering from Cornell University, Ithaca, New York in 2005 and 2006 respectively. In 2006, Udayan joined Applied Materials to serve as the technical lead for flash memory applications development at Applied Materials Front-End Product Division, Sunnyvale, California. He joined the Department of Electrical Engineering in 2010. He has authored and co-authored more than 40 journal papers and more than 75 conference papers. And also he has to his credit 25 plus patents applied and granted. His research interests are in semiconductor device physics and process technologies for advanced memory, computing and neuromorphic systems. He likes to experiment with teaching and learning methods like think, pair, share. Yeah. So we look forward to listening to his interesting lecture. Thank you.
So thank you very much, Professor John, for the very kind introduction. Thank you, Professor Kulkarni, for organizing this. So I'm very happy to be here, and really, it's exciting to come here, give a talk, and be recognized by the campus community and the very institute you serve. So this is actually a lot of work that was done by a motley crew of students and staff. So this is Sunny. Sunny finished his MTech here, worked for 4 years, rejoined the group and has pushed technology development. Piyush finished his PhD here, stayed for a year, and part of his work was to develop technologies for that is recognized in this project. Ashwin is sort of the youngest of the group. He's a master. He's a BTech student, dual degree student in the 4th year now, and he also has contributed. And this is Swaroop. He's sort of part of the mastermind. This is the group, and we have sort of tried to figure out how to do semiconductor technology development in India. So quickly, why electronics is critical to India? If you look at sort of on the right hand side, what you see is all the things that are extremely important for all of us, right? The security, healthcare, we have a large population, agriculture, pedagogy, which is education, and energy and environment. And I think one of the people from this institute coined the term shape, because this seems to be what would shape India's destiny. If you look at all these, then you have to say who provides or solves these questions. And on the other side is electronics and what that would contribute to each of these solutions. So there is sensors and Internet of Things, high-speed communications, big data, green energy, security and encryption. And really, if you look at sort of how things is going to evolve, we are going towards a more and more integrated world, right? Where everything pretty much talks to each other, intelligent decisions are made. And in every part of life today, I think electronics is essential, and because it's in every part of life, it is also ubiquitous, right? So this is for any society. What about India specifically? India is actually a very interesting case where we import about $100 billion worth of electronics, which is a lot of money. And our strategic import is roughly 10% of that, which means everything that secures us as a country is purchased or imported. A lot of it, actually, $10 billion worth of it, right? Per year, right? Every year you got to do it. What are our national needs? There are strong strategic needs. There is defense and aerospace. So electronic systems run our defense. They run our space program. When we want to make a smart power grid, the decisions are going to be made electronically. If you look at agriculture, e-commerce, banking, secure voting is an electronic process. It is no longer things that you cast a paper ballot at. So all critical infrastructure is essentially something that requires a very, very secure electronics. So how secure is electronics that we purchase, right? So these are sort of, you know, snapshots of news items that people have talked about. So how is your Chinese smartphone spying on you? It's possible because you have a billion devices, billion transistors, and you don't know if 5 transistors are leaking your information out. This is a news, I think, in 2000. I can't remember the date here, but fairly recent, which said that the Russian hackers could have caused the huge electricity blackouts in the US, which meant that an entire country's infrastructure could essentially be held hostage because electronics sort of provides a gateway into your infrastructure backbone, right? It's no longer manual controls. It's an interesting story here. So I think a lot of people know this, that during Kargil war, India had requested the US for satellite access. And we were essentially denied at a time of need. And essentially that has sort of spurred us to develop satellite technologies, our own navigational systems, GPS. And this is something that is pushing us. Recently, Intel chips came up with big flaws. So if you think of user data, that is one thing. Then there is a chip's kernel, which basically stores all its core instruction set. It turns out that during certain aspects, the kernel itself could be overwritten by external agents like hackers. So this is again an interesting thing that is happening. AMD fixes 13 of its vulnerabilities, right? So this is the problem. Electronics is the new oil, which is true. Essentially, our electronics imports are second to oil, and we really need secure wells, right? We really need our own layer of being able to do it ourselves going forward, and maybe then supplement it with commercial stuff, right? This is especially true for strategic imports. Okay, so this is where we started, and we've been sort of talking about this. There was a 2011 national electronics policy, which sort of wrote this, and as a group, which is our nanoelectronics group, we have been sort of trying to understand the social impact and the national impact of this, and figuring out how to solve it. So what is India's response to this? India has a very interesting lab called Semiconductor Labs in Chandigarh. It runs a procured, which means it bought about a 180 nanometer CMOS technology, which is a slightly dated technology, but it's not terrible. It's actually quite good. It was purchased at about thousands of crores of investment was done to sort of get it. But it is great, but it is purely a digital core. It does some little analog, right? Which means it can do some amount of analog digital conversions. But here are the gaps, right? So a foundry should be able to give you very fast communication chips, right? And this is something that our SCL does not have, right? It does not have very fast transistors, and so this is what you would need. A global foundries would essentially offer you this technology. One-time programmable memories. So the chip does not have a read-only. It does not have a memory. It has SRAM, which is transistors, right? But it does not have a non-volatile memory. You cannot download code and then let it be, right? And all this technology is very important for code storage, for electronic voting machines, and so on and so forth, where you just need to record everything once, and then that's it, right? You don't want the data to change. That is the identity of the chip, right? The third thing is hardware encryption. So if you think about every chip today, we are going to discuss this a little bit at length. the communication is between chips, right? And one needs to now think about this idea of, is your hardware encrypted, right? And there are a lot of implications for banking, commerce, all sorts of transactions. The last thing is a multi-time programmable memory. So you have a memory, you would like to, for example, you have hard disk, right? And today you have these flash drives. You want to sort of do a computation, put the result, turn off your computer, come back again, and then, you know, reload the memory, right? And that is a technology that doesn't exist. So even if you can make a microprocessor, you would need to get memories from external sources, right? So the goal has been for the group to do technology development for indigenous high volume manufacturing, right? That's been the idea. And so today, while we have sort of attempted to do all these four, I'm going to essentially focus on these two, which is one-time programmable memory and an application of that, which is hardware encryption. So what is the nature of encryption, right? So if, for example, there are two persons who are talking to each other, the server essentially provides an identification. For example, your chip has a SIM card, your phone has an IMEI number, right? These are numbers that are externally downloaded onto your device to identify them, right? So there's a possibility that at the server, somebody could essentially eavesdrop that identity, assign the same number to another computer or a cell phone, and now you have essentially somebody has cloned your phone, right? And your security essentially is compromised, right? So this is the concern. What is the alternative? The alternative is, what if your chip came with a unique number, right? What would that do for you? Okay? Now this is a very tricky question. In high volume manufacturing, the whole point is that every chip is identical, right? I make one design and I fabricate out a billion chips. All of them are identical to tolerance, right? So how do you therefore again assign or create, you know, individual chips to have individual IDs, right? So this is a sort of a conundrum, right? And if somebody does put in an ID, he knows it externally, right? So this is also a problem. So the ID has to be auto-generated inside the chip, right? Spontaneously, without anybody knowing about it. That is the challenge, right? And then once that ID is there, I can use some circuits, use that as a seed, and then do transactions based on the fact that this chip now has a unique identifier, and I'll leverage that. So every chip now ends up having a slightly a different unique identifier, and I can now do secure chip-to-chip transactions, right? And every identifier is unique and nobody knows about this, okay? So what are the problems with software keys? They are used for authentication. They are normally generated by vendors or programs, and they can be accessible by people, right? What is the solution? Is what is called a physically unclonable function, something that cannot be cloned. It is auto-generated internally in a chip. It's like your face or your fingerprint, right? Nobody controls it. It gets auto-generated. It is not in any design. It's not that there's a design for it and that's what you're building out. It is, again, spontaneous, right? It's a unique fingerprint, but again, you can't see it, right? It's maybe like your iris scanner or something. And it's externally unreadable, right? Externally, you can't see what it is, okay? So how do you do this? So this is sort of the big background of the technology. So it's very simple. So anything that goes into manufacturing has to be somewhat neat and elegant, right? It cannot be, you know, complicated, right? So we use a very sort of an idea that we are all used to. So that of a capacitor essentially. So this is a metal insulator metal, and this is not a capacitor in that I'm not measuring capacitance. What I'm doing is I'm measuring resistance across this insulator, and this is an open circuit, right? If I blow the capacitor, I will get a filament of some sort which will create a short circuit, right? So this is a low resistance state. If I put a voltage across this, a lot of current will flow. Now, the next piece of puzzle is that how does a filament get created? Are we familiar with that? And most of us are, right? All we have to figure out is the fact that if this filamentation is essentially the same as a lightning strike, right? In lightning strike, atmosphere breaks down. In a filamentation in a capacitor, the dielectric or the insulator breaks down, right? So what is interesting about this? Do you see the jagged edges of this lightning? Of course, this lightning is not controllable. It is actually a random phenomenon, right? A lightning never strikes at the same place twice, right? That's what people say, right? Why? Because it's pretty random. So the question for us is, can we leverage the breakdown randomness and therefore create a random ID? That was the idea. So what do? If you could essentially put a voltage across an array of these little capacitors, which are these blue dots, right? You would break a bunch of them down, right? But you do not know which one a priori, right? So it's not in a design, okay? So this is the idea. Now, normally, these oxides inside a semiconductor chip break down at very high voltages, right? So one challenge was to reduce the voltage, right? And the other challenge is after you've done a breakdown, it should not move, right? It should remain an ID for the chip forever, right? It should not move around, right? Or change its resistance. So here is sort of what happens to two devices, right? So they are perfectly identical. I apply a voltage in time, so the same voltage is being applied. And what's happening at the atomic level, right? At the atomic level, current is flowing, right? And some defects are being generated. What are defects? Defects are some places where one of the atoms has become displaced, right? And a current can therefore start flowing, right? Now, if an atom gets displaced, for example, there's a point defect, current will not flow. Why? Because there is no way for the current to cross the river, right? How will you flow it? Well, the defects get generated randomly, so it keeps on building, and then at some point a bunch of defects align and the current can essentially go from one electrode to the other. That's the idea, right? So the moment that happens, and this is a very random thing, you know, here it hasn't happened, here it has happened, and suddenly this forms a filament and the current starts flowing, right? Now this essentially means that this guy, the yellow one, has essentially sort of spiked high in current and the current is high now. This one is still building defects, right? And after some different time, this is going to spike, or this is going to short, right? So this essentially means that two random devices will take two different times, even if they're identical to begin with. Why? Because this defect generation process is stochastic, right? Okay? So when that happens, what you get is that over time, you can have a probability, right? So after some time, everything would have broken down, right? Below some time, nothing would have broken down. And around some time, there would be a distribution of breakdowns, right? So for example, the green one has happened here, the yellow one which has happened here, and they're different in time, and they would sort of sit on this line, right? Now if you set your chip time to say, look, I want to use this much time to break down, right? Then everything would have broken down. No problem. It is a deterministic process. I have put too much time. I can run this, right? So this is when I want a memory, right? I want to program every bit and I want it to be a 1. So I'll put a voltage, hold it for a long time and make sure it breaks down, right? Now what happens, so this is essentially memory, right? Now what happens if I want to make a random number generator? What I need to do is select a time somewhere here where there's a 50% probability that these devices would break down, right? What does that mean? 50%, any device below this would not break down. Any device above this would break down. a priori I don't know which devices would break down, right? So I will get a random bit, so there's a 50% chance, and I'll get it's impossible to guess which one is going to break down, right? So this is sort of what we did. These are breakdown voltages, and this is sort of voltage tolerance. So if you look at what the chip can give today, it can give about 3.3 volts. So one of the things we showed was that you can engineer the dielectric such that the voltage is less than 3.3 volts, and you can make a thin and uniform, and it still works in a production fab, right? That was the first thing. The second thing is that once they are broken down, so you have two states. I don't know if you can read this. There's resistance versus probability. So there are about hundreds, lots of about, I don't know how many devices are these, quite a few, maybe 100 of these, and 100 of these at low resistance state, 100 of these at high resistance state. And once they are done, even if you bake them for say 6 hours, I think this was 2 hours bake for 200 degrees Celsius, the bits don't flip. So they retain that information that they were broken down, and they don't heal themselves anything, right? Okay, so one big problem is how does, if in a chip your voltage supply can be only controlled to roughly 10%, right? So if, for example, you take this voltage and you take the probability and you say I want to do something at 50%, right? And this is a 50%. Now if I have a 10% variation, I am going to go up to all the way 90% breakdown, which means that essentially this is my ideal breakdown. This is black is open and white is short. Your breakdown looks like this. If there's a voltage change, your breakdown looks like this, which is most of them is one type. Hence makes it extremely predictive, right? I know most of them are black, right? Or short circuit, right? So what did we do? This was something that we invented, and so what we did was we took two of these capacitors and put a resistor, right? And we would apply a voltage, so the voltage would sort of be applied here, and this voltage is here. So this device would essentially start, defects would start forming. This one would essentially break down. The moment this breaks down, there's a large current that flows through this resistor. This would essentially drop the voltage across this resistor and arrest the voltage here. If the voltage drops, this will not further go into breakdown, right? So it's almost like a self-arresting or a self-saturating process. And once this happens, then no matter what your voltage variations, you are going to be able to have perfect 50% breakdown probability. So this was what we tested out. So this is the circuit solution, and this is sort of without the circuit solution. So you can see that as the voltage deviation increases, this one still remains at 50%, while if you did not do this, you would go all the way to 100%, and then your chip would not work. Your memory window is very large. It's about 10 to the power 4x, which is a large, so it's almost digital. It's better than digital. This is sort of this is called inter-Hamming distance. Essentially, if you had an unbiased coin, what would be the percentage of times it would do a 50-50 in a 10 time flip, right? So sometimes it would be 45% once, sometimes it would be a little bit less, and it would form this distribution, right? Now, if you took our device and you do the same thing, it essentially would mimic exactly an unbiased coin, right? Which is really nice. Again, this is sort of a 6-hour test at 250 degrees Celsius, and all this is data which is manufactured in the fab, right? So we got devices to run, we tested them, and so essentially these are production worthy, right? So then we went to DRDO and we said, can we help? Can we make this into a product? And they said, okay, look, you need to hit these specs, reduce the voltage, increase the size of the array, read and program this. We knew. They also said, if the chip gets captured, then you need to detect it. And once it's captured, you need to erase the chip. So you need some circuit tricks to now do that. So we formed a team. So SCL, IIT Bombay, there's some circuits people from IIT Delhi who work on this sort of area, and DRDO, and have sort of championed this. So this is sort of one example. There are 4 other technologies we worked on. First one was bipolar technology, and we sort of demonstrated that. This is what we discussed, the one-time programmable memory. This is encryption hardware, again this sort of unbiased perfect randomness. And recently we also demonstrated a flash memory, which basically does about 1,000 cycles, and it can change between bit 1 and bit 0. This is a very initial thing, but it is in the fab. It is not in our lab, right? So it's gone to that extent. So this is pretty much what we sort of did. We have sort of I think as a group our relevance has sort of increased based on this. So SCL essentially has invited us to work on technology development. Normally they buy technology outside, but this is an initiative that has helped us. For our large nano center proposal, about 2 out of 4 of the deliverables are based on this activity. We had a visit from ISRO chairman, and they want to come into our research park, acknowledging the fact that their biggest concern is electronics. IIT Bombay is presently been elected the Strategic Nanoelectronics coordinating institute for the large nanoelectronics center effort. This encryption chip is now sort of under technology development with DRDO as a chip. And finally, I think there is a push to develop an IMEC-like fab, and there is a request to basically ask us to sort of develop this proposal. So output. So we have had essentially 2 patents which are applied for, and there are about 4 papers. So technology development, but also this is something which is sort of cutting edge, and people across the world want to know about it. That's it. Some of it made it to the news, and this is again an IIT Bombay effort. But if you look at the team, these are all the people from Semiconductor Labs Chandigarh who have sort of helped run, and this is part of the team because it's an entire fab, and these are people who have sort of been our champions over at that end. That's it. Thank you very much for your attention.